Swayam Prabha. Digital India. Educated India.
Hello friends, so we are finally at the last lecture of this particular course where we were discussing about the topic of waste management and economics. So this is the 12th week of the course and this is the second lecture on waste management. We already had one lecture where you were introduced to some of the initial topics of waste management, and today we shall be finishing up this by discussing a few more points related to waste management. Of course, this is a topic which is highly relevant to the nuclear industry, and there are several newer technologies that is coming up every day. It is also a strong field of research, but also quite expensive research, because it is not easy for an individual researcher or even for an institute to deal with nuclear waste or to do extensive research on nuclear waste unless there is strong support from the government and corresponding nuclear agencies. And therefore, the research that goes on with waste treatment or management of nuclear waste is generally quite confidential in nature, and every country has their own ways of managing the waste depending on their own policies and their own research observations. That is why, despite having a quite decent volume of material on this waste management, or despite this being a quite active area of newer findings, we have to restrict ourselves only to the fundamental concepts of waste management and most major discoveries or most important type of definitions under this field. In the previous lecture, you were of course introduced to the sources of radioactive waste. We have seen that it is not only the nuclear reactor which produces radioactive waste, rather we can have such kind of waste from several other sources. Starting right from the point where nuclear material, something like uranium, is harnessed from the mines, we have waste production. In fact, mines are the largest contributor from volume point of view for the radioactive waste. From the mines or from the subsequent milling process, we get the mill tailings, which comprises about 90% of the total volume of radioactive wastes, though the corresponding radioactivity can be quite small. We can also have radioactive waste production during several other stages of the fuel cycle, like during the enrichment process, the spent fuels which comes out of the reactor during the reprocessing part, or subsequent downstream application, if any. We can also have radioactive waste production from medical fields, which is actually a growing contributor in this particular segment. And there are several other industries also which make use of radioactive nuclei, and hence they also contribute towards the radioactive waste. We may have some kind of waste production from researchers as well. Then we had to go for a classification, because the way we are going to dispose radioactive waste depends on the classification. Different countries have their own methods of classifications, but we have selected the one that is suggested by IAEA, that is International Atomic Energy Agency, who classifies radioactive waste into 6 categories, starting from the exempt class, which are having insignificant amount of radioactivity, to the high level waste, which are the strongest contributor to the radioactivity. Volume point of view, high level waste may be just about 3 or 4% of the total volume, but can contribute about 95% of the total radioactivity, and hence we need to be very careful about their own disposal. Then we discussed about the mill tailings. The source of mill tailings were discussed. Just something that is quite relevant to that, the heap leach recovery, which is another process of producing uranium, but a different method, I should say. But then after the process is done, what is left, that is quite similar to the mill tailings, and then we have discussed about the procedure of disposing the mill tailings. there are several approaches that were attempted earlier to dispose the mill tailings, but also as we go on with time, we gained experience about how we should dispose, what are the methodologies or the principles that we should follow while disposing the mill tailings, and also we got more information about what are the possible hazards that we may have the mill tailings. Like there can be radon emission and radon getting mixed with the soil and air and earth, which can strongly contribute to the carcinogenicity in the human being. We can have arsenic. Arsenic can have its own radioactive decay, or itself also is strongly carcinogenic in nature. Then we can have seepage of radioactive materials like uranium and arsenic into the groundwater and soils, and there are several other kinds of effects, and that is why you should be very careful about this. Despite having low level of radioactivity, you should be very careful about disposing the mill tailings. And this diagram shows one of the proper mill tailing dams that are used nowadays. It is generally widely accepted that we have to go for underground disposal and also disposal under water. That is, the tailings should be under a body of water, but that water also should be separated from the tailings by several layers of barrier. Then such kind of tailing ponds again can have different kinds of classification, like we can have upstream tailing ponds, downstream tailing ponds, or center tailing pond, depending upon how we are increasingly adding more dikes. Each of them has their own advantages and disadvantages, which we have discussed. So today we have to go for the discussion of different other kind of radioactive wastes, those high level or intermediate level particularly, and then find a few possible methods of disposing those kind of radioactive wastes. Now this is one diagram which basically quantifies all those radioactive wastes. Yesterday itself we have seen that commonly we can have 6 different kinds of radioactive waste as per the IAEA guideline, where the first one is the exempt class, and in this diagram we are quantifying them using their activity level and the decay period. Exempt class refers to something that is having extremely low activity level. It is so low that we can just forget about the radioactive effect and dispose it like we do the garbage disposal or any other industrial waste disposal. Then we have very low level waste, that is again having a very short activity level, and whatever radioactivity they have, generally they contain quite short lived radioisotopes which can lose its entire activity within a short period of time, maybe a few days or weeks, and after that. So we basically need to contain this very low level waste only for a short period of a few weeks or maybe a couple of months, and then it can be disposed just like the exempt waste. But then we have the low level waste, which this LLW and VLW are the largest contributor in the radioactive waste disposal technique. Particularly those mill tailings, they invariably fall under the category of VLLW or LLW particularly. So their disposal methods are also quite same. And on this side we have another thing, something called the very short lived waste. These are again the radioactive wastes which are having extremely short life, so their activity level can be quite high, but generally that spans over only a very short duration of time. So we generally don't need to bother about them after a few initial periods of activity. But the major concerns are related to this ILW and HLW, both having significant radiation effect. ILW, while the half life can be quite large and also the radioactive level can be quite large, but the energy contribution, that is the heat produced because of their decay, is generally insignificant. So while we need to be very careful about radiation protection while dealing with ILWs, we don't need to bother too much about energy removal or heat removal. But in case of HLW, the radiation level is also high and also the energy release rate is also extremely high, and therefore we have to provide the dual option of radiation protection plus cooling or heat removal. So handling HLW is very difficult. ILW also needs to be handled properly. Another interesting thing we can see here, like if we follow a particular radioactive level or say a half life, while we are moving in the upward direction with the increasing level of radioactivity, we are getting from EW level to the HLW level. But if we draw the same line horizontally, something from here, Again, for a given activity level, as the decay period is increasing, we are moving from the very short lived isotopes to intermediate, or in certain situations maybe high level isotopes as well. So, whenever you have a radioactive waste to deal with, first we have to identify exactly where we stand from this chart point of view, whether we are somewhere here, or whether we are somewhere here, or whether we are somewhere here, and accordingly we have to decide our mode of disposal. Like if we are dealing with a low level waste, then we can dispose it only with a minimum amount of containment, maybe for a short duration of time. Whereas, when we are dealing with an intermediate level waste, we have to provide strong radiation protection, good amount of containment, but we generally do not need to provide any kind of cooling methodology or very small amount of cooling. But when we are dealing with HLW, radiation protection should be the strongest, plus we also have to provide adequate amount of cooling, because it is going to reject large amount of heat because of its radioactive decay and over a significant period of time as well. This is some kind of projection which shows what is the expected volume of radioactive waste in the year 2150, that is about 130 years from now. So, that is very much a projection. So, we can see that as per this projection in 2050, while the amount of very low level waste will be something like this, 2720 into 10 to the power 3 meter cube, corresponding radioactivity will be only 14 terabecquerel. So, that is extremely small. Like if you think about the conversion between becquerel and curie, I hope you remember what is the definition of 1 curie? That refers to the activity level of 1 gram of radium-226, and that is 3.7 into 10 to the 10 disintegration per second, whereas 1 becquerel is just 1 disintegration per second. So, that is a very small unit. So, 1 terabecquerel is only of the order of 100 curies, which is not, which of course is important to be important to isolate that amount of radiation from the human being, but still that can be handled quite easily. But when you go to the low level waste, you can immediately see the expected volume of this low level waste is about 60% of very low level waste, but there is about 6 times increase, 6 to 7 times increase in the corresponding activity level. While dealing with the storage or disposal methodologies, while developing a new disposal site, we have to first decide what kind of material we are dealing with, and if we have decided that it is going to be for low level waste or very low level waste, then we have to provide very large volumes. But interesting thing is that we may not have to store this waste material for a very long duration of time, maybe only for a short duration of time we have to store them, and once it loses these activity levels, then we can dispose it. But that is not true for the intermediate levels. Now, first compare the expected volume. Here it is less than 1/3 of the low level waste, and less than 20% compared to the very high low level waste. But look at the change in the corresponding activity level. It is a change of the order of 10 to the power 4 times, which is a substantial increase. And finally, when we move to HLWs, then the increase is again about 6 times compared to ILWs, while the volume is reduced to a minimal quantity. And now, if we combine all these volumes, these projections, if you see that the total volume of HLW that we are getting, that is only a very small percentage, just about 1% or even less than that of the total volumes of all these kinds of radioactive waste. But the radioactivity that it is providing, that itself is so high that we can almost neglect everything else. May not be the intermediate level waste, but we can easily neglect the effect of VLLW and LLW, and therefore, we may not have to provide large amount of storage for HLWs, but that needs to have very strong amount of containment. Now, from where we get which kind of waste? Like if we always think that nuclear power stations is the most common source, but if we think about that, now from the power stations we can get low level waste. This is the low level waste that we actually from power stations we get all different kinds of radioactive waste. From different parts of this we may get different kind of radioactive waste, like the structure of a nuclear power stations, the outside structures, the reactor building, etc., which are made of concretes or metals, they generally get only very small amount of radioactivity, which may get sprayed through the coolant or may be coming because of the ionization radiation leaking out of the containment structure, the gamma radiations, etc. And so these concrete structures or metal structures may become radioactive, but the concerned level of radioactivity will be extremely low. Then as we move inside, the solidified waste liquids, the liquids, the filters, scrapped equipment, several consumables which are used in radioactivity, they also are generally in the level of LLW. So, the concrete or metal structure that we are getting, they are in the level of VLLW, very low level waste, and whatever radioactivity they may get, of course, the concrete structure is going to stay with the nuclear power stations, and we remove them only once they get damaged or only during the decommissioning of the plant. So, when we are dismantling one nuclear power plant, then this concrete structure gets separated, but the radioactivity level is so low that only a few days or weeks of containment is sufficient to remove entire amount of radioactive effect. But the solidified wastes or the scrapped equipments or consumables which regularly get produced from the nuclear power station, we have to provide some kind of continuous treatment for them, and they fall in the level of LLW. So, their radioactivity level is also low. They require some amount of containment, some periods of isolation. Isolation means we need to separate it out from the human beings and any other living beings for a reasonable period of time, and once that quarantine period is over, again that can also be disposed of. But now comes those structures which are inside the reactor itself, like the control rods, like the reactor stainless steel body itself. They are directly exposed to the reactor nuclear fuel, like the control rod material is absorbing a large amount of neutrons, and thereby they may become radioactive themselves. The reactor structure is also receiving the neutron bombardment. If they are also receiving several other kinds of decay which goes on, the decay of the fission products, and corresponding all those beta and gamma emissions may lead to the ionizing radiation of the nuclear reactor structures, and so we generally reach the level of ILWs, intermediate level radiation. So, for these structures we have to provide a much better amount of containment, and we may have to store it for a few 100 years as well. And finally, the high level wastes. Interestingly, from the nuclear power station we may not get the high level waste. Rather, the major production site for high level wastes are the reprocessing plant. The spent fuel is taken to the reprocessing plant, and there by supplying other processed fuels, etc., we can convert the spent fuel into some usable product, like we can separate out the uranium part from there, and corresponding uranium oxide can be sent back to the reactor. We can also separate out uranium and plutonium and fabricate MOX, that is a mixed oxide, and that can also be used as a fuel. And what is left after that entire process of reprocessing or refabrication, we need to dispose it, and these generally are high level radioactive wastes which contains several heavy nuclei which emits alpha radiation and also can have very long half lives. So, we need to store them with the maximum amount of containment and also for a very long period of time, which may be a few hundreds years. Particularly the liquid waste that comes out of the reactors or from the reprocessing plant particularly are of major concern, because handling a solid fuel is much easier compared to a liquid fuel, because if there is any small crack in the containment structure, liquid can leak out of this and lead to the spreading of radioactivity, but which is not true for the solid fuels. So, while from the nuclear power plant we may get different levels of waste starting from VLLW to ILW, we generally get the HLWs produced from the reprocessing plant. Also, these are only the nuclear power stations that we are talking about, but there can be other sources. Several medical equipments contribute ILWs and HLWs. The nuclear weapon program can have significant contribution to the HLWs. Also, if there is any nuclear testing that happens, the contaminated site or the corresponding site may get contaminated by the HLWs, leaving all the neighboring areas to be vulnerable. Now, the principle and philosophy that we follow during disposal of nuclear waste should be very clear to the operator, and accordingly IAEA has set out these philosophies. Firstly, the protection of human health and environment means the radioactive waste shall be managed in such a way as to provide an acceptable level of protection for human health and the environment. Under no situation the human health and the environment should be put under a threat, even a minor threat. So, we have to remove every possible bit of radiation, and so whatever waste is there we have to dispose that. Secondly, the concern for future generations. It is not that at this moment we have disposed it with whatever we felt is the best one, and say 20 years from now it starts to create a huge massacre. We also have to keep an eye on the future. The waste shall be managed in such a way that it will not impose burden on future generations, and its predicted impact on the health of future generation will not be greater than relevant levels of impact that are acceptable nowadays. Third principle is the establishing the legal framework. The waste shall be managed within an appropriate legal framework, including clear allocation of responsibilities and provision for independent regulatory functions. And finally, the waste minimization, management, interdependency and safety of facilities. As waste itself is very much hazardous, so we have to make every effort to ensure that the quantity of waste that we are getting, that is kept to a minimum possible. And once the amount of waste is small, waste produced from the facility is small, the effort required to manage that time required for its complete radioactive decay is definitely much less. The interdependency amongst all steps in the radioactive waste generation and management shall be taken into account. The safety of facilities for radioactive waste management shall be assured during the lifetime. So, these are a few principles which the operator or agencies must follow while devising a method for radioactive waste disposal. Now, methodologies of disposal, there are 4 clear methodologies or 4 clear kinds of methodologies that are followed by different agencies. The first is dilute and disperse. Each is particularly relevant to low level wastes, especially those coming out from the medical facilities, like those who have gone for some kind of X-ray treatment or other procedures in the hospital. So, the waste that we get from such kind of low level wastes, they are diluted to a level such that concentration of the radioactive material in water becomes negligible. So, we add this radioactive material to a huge volume of water so as to reduce the concentration of radioactive material to an acceptable limit, and then that water stream can be released to the environment, to some larger body of water, and it is expected not to be any detrimental to the environment. But it is true only for the low level waste. We can't apply this for high level waste, because high level waste not only have a stronger level of radiative activity, but also a very large half life, and so they will contain the radioactive effect for much longer. Hence, this method of dilute and disperse is limited only to the low level wastes. Then the concentrate method, it is the opposite. Instead of diluting the radioactive waste, here we go for concentrating that into the smallest possible volume, and this is something that is suitable for very toxic and highly radioactive wastes. In concentrate method, the radioactive nuclear waste is locked into crystalline structure of rock synthesized by the scientists. On not only rock, we can have a few other kind of structures also, we shall be seeing shortly in the next few slides. The radioactive waste can remain in this form for millions of years. It is one of the safest method of disposal for nuclear waste, provided we can make enough option of the radioactivity or radiation containment and also cooling. That is, the energy produced by the continuous radioactive decay of these wastes should be taken care of immediately. Then the delay and decay, that is used for disposal of intermediate level waste. In this particular method, the radioactive material is allowed to move through the soil. We know that their activity period is lesser compared to HLW. So, we allow them to move through the soil. During the slow movement, it decays, and beyond a certain period of time, it reaches some agreeable or acceptable level of radiation, and so can be allowed to mix with the soil freely. And finally, a next gen technology, the space disposal. It is probably the safest way to get rid of the nuclear waste, because we have infinite space available in the outside our biosphere, and therefore, it is possible that we load the nuclear waste into a space shuttle and then launch that into the outer space. Once the shuttle goes out of the stratosphere of the earth, then it is the mankind is completely safe from the radioactive wave of that particular shuttle, radioactive decay of the material stored in that particular shuttle. But it has its own issues as well. Once it decays in the outer atmosphere, we do not need to bother about that, whether the half life is small or half life is large, it does not matter. But during this transfer process, firstly the space shuttle itself is very expensive, and one shuttle can handle only a small quantity of nuclear waste. So, large number of shuttles will be required, and secondly, there is always a danger of shuttle exploding, which would if it happens at all, then it will contaminate the neighborhood air, and also further damage will happen. So, these are the principal methodologies which are followed during the disposal. The dilute and disperse method is primarily followed for the low level waste, delay and decay is followed for the ILWs, whereas concentrate method is more suitable for the high level waste. And this is a chart which shows the same thing. Like when we are dealing with the high level waste, we need to be very careful, and that is why the most common technique is to go for deep geological disposal, at least at a depth of 500 meters. And the intermediate level waste, surface disposal facilities can be there, or we can also go for intermediate level disposals quite similar to the HLWs, deep disposal at 500 meters. For LLWs, you can stick to near surface disposal, that is any natural source like a mine pit or some natural tavern kind of thing can be allowed to store the low level waste. And for the very short lived wave, generally you do not need to bother about the radioactive decay, because their radioactive decay period is quite short there, because the half life is short. So, they can decay very quickly and can lose its entire hazardous effects within a few weeks or even within a few days. So, we do not need to bother about their disposal that much. Now, let me introduce another new term. Of course, so far we are introduced to all these terms, that is very low, VSLW, LLW, HLW, ILW, etc., and also I have missed this VLLW, very low level waste. They hardly have any kind of radioactive effect, and that is why we can dispose them like the normal garbage. So, they can go for surface disposal. But all these 6 kinds of terminals that we have followed, they are given by IAEA. But there is another very commonly used term, that is transuranic waste, which is generally used only by United States. Transuranic waste refers to the wastes which are artificial and also heavy nucleus and heavy alpha emitting nucleus. The atomic numbers of the principal element should be greater than that of uranium. So, the term transuranic by default refers to something having atomic number higher than uranium, such as neptunium, plutonium, american and others. Curium can be another example, and because they are heavy, their atomic number is greater than 80. So, they are most likely to go for alpha emission, and also we have to remember that uranium is the heaviest naturally found isotope. Anyone having atomic number higher than uranium, that is from neptunium onwards 93 atomic number, they are all artificially produced. So, it has to be something that is heavy and artificially produced. Then half life greater than 20 years. If half life is less, then we can go for very short lived storage. If half life is less, we do not need to bother that much about them, but if the half life is more, then we have to store them properly. And finally, the concentration should be greater than 100 into 10 to the power minus 9 curie per gram or 3.7 megabecquerel per kg. So, just having 1 or 2 isotopes will also not do the solution. Just having a few small nuclei which does not give that amount of concentration will not guarantee something to be called transuranic. All these 4 conditions needs to be satisfied. Transuranic waste is primarily produced from the recycling process, and the nuclear weapon program and also nuclear research. The nuclear weapon program is the biggest contributor to the transuranic waste. There are several countries who have very strong nuclear weapon program, and that is why they produce a good amount of transuranic waste. While the term itself is recognized only in United States, there are other countries also which get similar level of waste. Transuranic waste essentially is a high level waste. That is why other countries do not use this term, rather such kind of waste materials are directly categorized as HLW, but this is one term specifically used by US, particularly related to their nuclear weapon program or corresponding research. And materials which are associated with such kind of equipments like protective gears, tools, residues, debris and other items that are contaminated with small amount of radioactive element, particularly plutonium, all are transuranic. US law further categorizes this transuranic waste into two categories. One is the contact handled or CH, other is remote handled or RH, on the basis of the radiation field measured on the waste container surface. The contact handled one has a surface dose rate not greater than 2 millisieverts per hour or 200 millirem per hour. But when you are talking about the remote handled, there the surface dose level is much high. It is in the range of, I think I have a mistake here, it is not m, it is just 2 sieverts per hour. So, it is at the level, oh okay, sorry, actually here we are talking about the transuranic waste which is having a dose rate of greater than 2 millisieverts per hour, or whereas for in case of CH it is less than 2 millisieverts per hour. So, the value was correctly written, but practically this RHTRU, that is remote handled transuranic waste, can have radiation dose value which is much higher than this, even in the range of 5 to 10 sieverts per hour. So, there are definitely high level wastes. The contact handled one, that is CHTRU, is not the high level waste, nor its generation is significant. Therefore, it can be treated either as ILU or ILW or sometimes even as LLW. But in case of RHTRU, it can be highly radioactive with surface dose rates can reach in the level of 5 to 10 sieverts per hour or 1000 rem per hour. Therefore, the handling of transuranic waste is also of extreme importance. This is one typical example of production of TRU. From the uranium mine, whatever ore that we get, that goes through the enrichment and fuel fabrication process, and after the fuel fabrication is done, this is the part from where we get the mill tailings. Now, after the fuel fabrication is done, this fuel assembly goes to the nuclear power plant. From the power plant, after the operation is completed for one cycle, this goes to the fuel assemblies, and then it comes as the spent fuel in the recovery or MOX fabrication plant, and the recovery uranium is directly fed back to the enrichment process. Now, the production of HLW, as mentioned earlier, is most likely to be from this reprocessing and replenishment unit, whereas the TRU, they can also get produced from this particular component, but they can also get produced from the MOX fabrication plant. So, HLW is primarily coming out of the reprocessing unit, but I repeat, the TRUs can get produced from the reprocessing unit or during the MOX fabrication as well. That is why they have strong amount of plutonium presence in them. Now, how to get them back to the reactor, or I should say how to the waste that we are getting, HLW or TRU. Now, how should we dispose them? A small scheme is shown here. First, we have to convert that to a canister, then put that in the drum. Those drums will be put into the rectangular container, and then it is going to get to the disposal facilities. The waste isolation pilot plant of New Mexico, United States is an example of kind of. I do not want to go to the details of this, but this WIPP is the most regarded facility for disposal of both LLWs and ILWs, and also the transuranic waste. It has different segments, some part handles TRUs, some part handles ILUs. Now, the HLW disposal. Despite continuous reduction in activity with time, HLW and TRU remain radioactive over a very long period. HLWs, as I have already mentioned, have very long half life, and therefore, as the radioactivity decreases asymptotically, still it will become strongly radioactive even say a few hundred years since the point it was first disposed, and therefore, it is necessary to isolate this waste from human intervention for very long duration of time. Different methods of disposing this waste has been investigated by the international institutions and countries, and it is a common consensus that we have to go for geological disposition in a stable host rock deep underground. So, this is the flow chart. This from the reprocessing plant we are getting these HLWs and the recycled which also during the MOX fabrication part we may get HLWs, but those are generally TRUs. So, the waste that we get, this waste generally comes in the form of liquid, and to that we add some kind of glass fabricating materials. So, that we get through glass fusing furnace we are able to produce solid glass, or we are able to convert this waste material into solid glass, and these glasses are covered or enclosed by stainless steel canister. So, the material converted into solid glass form is covered first by solid stainless steel canisters. Next, these canisters were put into a proper structure where each of the solid glass element are covered. Okay, let me show another picture here. This is the vitrified waste. Vitrified refers to the waste converted to the glass form, and then it goes to the steel container. Look at here, the thickness of the steel container can be as much as 20 centimeter. So, it is quite thick, 20 centimeter we are talking about. And now, this steel container, actually in between the steel container and this vitrified glass we may have some kind of buffer material also, which is the compacted clay, or I should say outside the steel container. First we have the vitrified waste in the form of glass, then covered by steel container which is covered by buffer material which is compacted clay. And now, this entire structure is arranged in a matrix like this, which is receiving continuous supply of cooling water and maybe sometimes cooling air as well. And finally, this entire facility, this entire block that is disposed to a depth of, this diagram shows 300 meter, but generally for HLWs and TRUs we go to a depth of more than 500 meters. Look at this, this is the steel canister, and then it has been covered by the waste package on every side with, and the in between portion is filled with some kind of filler. This underground facilities that we are talking about, they have their own buildings, like there are tunnels for transporting and placing these waste packages, and they are constructed in a stable host formation more than 300 to 500 meter underground, and the facilities required for supporting underground exploration operation and closure of the repository are also constructed. This is a typical site. This is an inclined shaft from where the underground or all these waste packages are put in the underground tunnels. The underground facilities, this is the ground level. From the ground level we are going downwards. This is the portions where we have all the channels or tunnels, I should say, where these waste packages are disposed with proper supply of cooling material. Look at this, over we are going to a depth of something like 300 meter. This is a location where HLWs are disposed, and at the similar depth TRUs are also disposed. Generally the TRUs are smaller in volume, because here we are referring to only the isotopes which are heavier than uranium, but HLW can contain several other isotopes as well. And all these construction facilities, they are carried out underground, means we have to construct the tunnels, then we have to fill up those tunnels using these waste packages, and then we have to backfill those tunnels. This everything needs to be done underground, and all these processes or all these operations should be properly parallelized or should be properly synchronized, so that as soon as we have one tunnel ready, we can fill that up with waste packages, and immediately we can backfill that tunnel and we can start operating on another tunnel. So, proper synchronization is absolutely essential, otherwise there will be chances of some kind of radioactive decay or leakage. ILW disposal is much easier. because ILWs, while the radiation level is still significant, we do not have to provide any kind of cooling option, and therefore, this ILW material can first be converted to generally in the form of chemical sludges, or rather this the ILW materials that we get, they are generally in the form of chemical use sludges, the cladding materials of the fuel, and certain other substances. So, the first these waste materials are converted or packed into steam drums. These are the steel drums, solid metal drums, and these drums are then dumped into concrete casks. So, this white portion that is shown here, this portion refers to this concrete casks. Then these concrete casks are put inside a concrete trench, and then the trench is covered with a layer of compacted clay. This entire facility is then put at a depth of at least about 100 meters or so. So, ILW we can dispose up to a depth of 100 meters, but for HLWs or TRUs we have to reach to a level of at least 300, preferably 500 meters, and you can understand the corresponding level of effort required to reach an underground depth of 500 meters. And also it is not that once we have gone to that depth and disposed the material, everything is done, we can completely fill it up. Rather, we need to keep an option so that we can go back there and we can continuously observe what is happening there. So, these are the primary classifications based upon the activity level, and based on different kinds of classifications we have also seen some of the methods of disposing radioactive waste, but there are a few other classifications for the purpose of completeness. I am providing them, like sometimes we also classify radioactive waste as defense and non-defense. As the terms are self-explanatory, as the defense waste refers to the waste produced due to military activities, the weapon program and corresponding research reactors, whereas the non-defense is primarily contributed by the medical and the power production facilities. Based upon the time when they are produced, we can also have front end waste. Front end refers to the initial part of the fuel cycle. These are produced during the fuel processing and enrichment and fabrication parts, which are primarily the depleted uranium and radium, and falls under the category of ILWs or LLWs. Then we have the service period waste, which involves the spent fuel rods. They are also generally in the intermediate level, because spent fuel rods generally have very small amount of fuel left at the end of say 1 year or something like of operation. And finally, the back end waste, which is of major concern, because at the back end during the reprocessing part we get the long living heavy isotopes such as uranium 234, neptunium 237, plutonium 238, american 241. All of them are strongly radioactive and also have quite long half life, and they are strong beta and gamma. These are heavy isotopes which go for alpha emission. We also get several other isotopes which are lighter, but have strong beta and gamma emissions. So, this back end waste, which primarily constitutes the HLWs, are something that needs to be properly disposed, and generally the HLW disposal methods are the ones that are applied to them. Depending upon the physical state also, we can have a classification, like you can have solid waste. Solid waste are disposed, they are easiest to dispose, I should say. Generally, like we have shown recently, the HLWs are vitrified to convert to glass form, solid glass. So, solid waste disposal are much easier after suitable conditioning. Depending upon the activity level, they either go to the near surface disposal, like in case of LLWs, or about 100 meter depth for ILWs, or maybe at the level of 500 meter depth in case of HLWs. Medical applications can also contribute significantly towards the solid waste, like papers, plastics, glassware, equipment, animal carcasses, etc., and other biological waste, that all can come from the solid waste category. Liquid waste is something, the handling that is much more difficult. Generally, the liquid level are low level wastes, that is, if their radioactivity level is low, we can directly discharge it to the environment after a few days of containment or suitable effluent treatment. But if their activity level is high, they are much more complicated to handle. The treatment system, this effluent treatment essentially comprises chemical treatment, evaporation, ion exchange, filtration, etc. like one diagram we have seen during the previous lecture, without going into the detail of that. Medical field is again a significant contributor to the liquid waste. It comprises both aqueous and organic streams such as the patient's urine and other kind of fluid, patients which are getting some kind of radioactive treatment like the thyroid cancer therapy, etc. Their excretion can contribute to liquid waste, and also the effluents from decontamination process can contribute to the liquid waste. The containment system for liquid waste, despite low level of activity, should be very strong, because a small leak in the structure and the waste can come out and spread radioactivity directly to the environment. Finally, is the gaseous waste. They are generally created or produced during the production and radio labeling of chemical compounds and organisms, during the production of radionuclides, and also during the treatment of the solid and liquid wastes. Generally, these wastes are treated at the source of generation and allowed to discharge to the environment through very tall stack, something having 100-meter height or like that, after filtration and dilution with continuous monitoring of radionuclides, and of course, it has to comply with the environmental regulation limits as well. So, these are the classifications based upon the physical nature, but again all of them can be classified as HLWs or ILWs or LLWs, and primarily all the disposal methodologies follow that IAEA classification, which is based upon the activity level. These are a few common disposal sites of the world from US, from France, Spain, Argentina, Australia. Every country have their own disposal sites. This is another from South Africa, a very common site. You can see from this diagram the different levels of protections that they have provided, different layers of protection that they have provided to get the radioactive material in the underground location and to stop any kind of radiation effects. So, that brings us towards the end of this particular module 12. Here we have learned and discussed about the radioactive wastes. We have seen that the waste can get produced during different parts of the fuel cycle, not only from the reactor, but also from the milling process, the fuel enrichment process, the replenishing and reprocessing part, and also several other industries can contribute to the radioactive waste. Waste can be classified from exempt to cast to HLW based on their activity level, and their disposal methodology is strongly dependent on their classification. Mill tailings, which generally falls under low level or very low level waste, but they are largest in quantity, can contribute up to 90% in its volume, but radioactive waste is very small, less than 5% or maybe in the 5 to 10% range. Disposal of HLWs and transuranic waste is of major concern. The volume is very less, can be just about 3% of the total waste volume, but can contribute about 95% of the total radioactive waste, and therefore, we have to provide extreme conditions for extreme care for their disposal, like several layers of protection, underground depth of 300 to 500 meters, and also the cooling options, and also very long period over which this is maintained. Disposal of liquid waste is more complicated, as there is greater possibility of leakage and spreading of radioactivity, and space disposal is a very prospective future option, but has its own challenges because there can be political issues as well, and also if this after the spacecraft has been launched, it is not fully in control of the operator. If there is any accident happens, then the radioactivity will be directly spread to the environment. So, we have to think this, or you have to be very careful about applying this space disposal. That is the end of our module 12, and at the same time it is the end of this particular MOOCs course on fundamentals of nuclear power generation. I do not know how to express, but it was an association for 12 weeks, during which we have discussed about several things. I have received several messages from you discussing which contains your queries. Some of the messages were praising the course, some of the messages which mentioned about the problems that you are having. I have tried to address those issues, like you are having major issues about solving numerical problems. I have tried to address that by providing the solutions. Hopefully, you are in a much better position now to tackle relevant numerical problems. While some of the topics we have discussed quite extensively, like the fundamentals of nuclear reactions, the neutron moderation technologies, neutron diffusion, neutron nucleus interactions. Several other cases also I have restricted myself, those more practical in nature like the fusion technology, the breeding reactions, radiation protection, the waste management here. All these are very practical methods, and there are several other things I could have included, but this being only the first course on nuclear engineering, I have restricted myself. If any of you are interested about any of those topics, you can go to the internet and search for materials. There are infinite resources available to learn. And also, while this course ends here, if any of you are interested about interested to know any relevant topics, you can always contact me. My contact details are available on the IIT Guwahati web page, so you can always get in touch with me and let me know. And please give your feedback. Means at the end of the course, what you have at all learned from the course, whether you have gained at all gained anything from the course or not. Please let me know, because actually this was a new experience to me as well. This is for the first time I had this experience of teaching in an empty room in front of the cameras and monitors, but no student in front, so I am not able to have direct eye contact with you, not able to interact directly with you, which is quite boring to me. I personally don't like too much this slide or presentation mode of teaching. I am a bit in the old mode, go to the blackboard and do everything there. And that is why while I was very much excited while preparing the slides, put my best effort to decide what to put in the slides, how to organize the slides, but during the lectures quite often I lost my energy. You may have seen me dozing during some of the lectures also, because I felt bored just talking in front of cameras. But hopefully I was able to get across some of the fundamental ideas, and if even some of you have understood a few aspects of nuclear power generation, I would think that is the success for me, this course. Again, another final request, please give your feedbacks. You can give the feedback on the course web page. You can also write personally to me about regarding what is your own observation about this particular course, because that will help me in similar kind of future endeavors as well. So that's it for now. We may meet in future in some other platform, maybe in another MOOCs course, or maybe some of you may come to IIT Guwahati as a future student, or maybe somewhere else just accidentally. If that happens, please let me know. I shall be very happy to. And also, if you need any kind of help, academic help, that is, any time in future, please let me know. I shall try my best to help you out. So, thanks a lot for the final time.